Hello everyone, my name is Shoaib Mahmood and along with my project partner Mir Faisal Tarif, we are pleased to present our project. Our project title is Smart Wind Tracking System for a Real-Time Wind Turbine Alignment and Power Optimization. Now extract. In this project, we addressed one of the common issues in horizontal axis wind turbine, which is yaw mechanism. So yaw mechanism leads to reduced power output and increased mechanical strain. We developed a real-time wind tracking system that uses a wind vane and anemometer to monitor wind direction and speed. An Arduino Uno processes this data and adjusts the turbine's nacelle orientation using a stepper motor. This system continuously corrects the yaw angle to ensure maximum energy capture and reduce wear on mechanical component. Now introduction. As global demand for clean energy rises, wind power is becoming increasingly significant. However, fixed or slow reacting turbines often suffer from misalignment with wind direction, which decrease their performance. So our solution is to maintain dynamic alignment using real-time sensor data and microcontroller based control logic. By doing this, we aim to maximize energy efficiency, reduce structural stress, and ensure long-term turbine durability. Now, research background. Many researchers have explored similar challenges. For example, OV and High team proposed a cost-effective smart wind turbine system featuring a yaw mechanism driven by stepper motors. They used machine learning model to estimate wind direction, significantly reducing the need for expensive sensor system. This innovation demonstrates a practical use of embedded intelligence for small-scale renewable setup. So, how our system will be worked? So, our system will be worked by using wind energy to turn the turbine blades, which then power a generator through a gearbox. The electricity produced goes to a charging unit that either store in a battery or power a DC load. Wind vane check the wind direction and send the data to the controller. If the turbine isn't facing with the wind properly, the controller turns the nacelle using a yaw motor to fix its direction. This keeps the turbine aligned for maximum. Now, methodology. We divided our work into four main phases. First, we analyzed the theoretical power available from wind. Then we will build a stepper motor based simulation for yaw adjustment. Next, we will develop a real-time control system using Arduino and sensors. And finally, we will integrate and test the full. This flowchart illustrates the control algorithm for an automatic yaw adjustment system used in wind turbine. So the process begins when reading the wind direction from a wind vane sensor and wind speed from a wind anemometer. If it then calculates the yaw error, which calculated the difference between the nacelle's current orientation and the actual wind direction. If the wind speed is greater than or equal to the cut-in speed, then the system will check the yaw error. If the yaw error exceeds 15 degrees, the yaw motor will be activated in the appropriate direction to align the nacelle with the wind. After repositioning, the nacelle's estimate positions is updated. If error will less than 15 degrees, then the system delay or hold the current position, ensuring efficient and safe turbine operation. This approach enhances wind energy capture by continuously aligning the turbine with the optimal wind direction.
Thank you, Shoaib Mahmood. Now I am starting this slide, that is wind energy calculation. To understand the importance of accurate alignment, we calculate the available power in the wind energy using the equation. Equation is P equals to half rho A V cube, uh, where rho is air density, A is the rotor swept area, V is wind velocity. This equation shows that power output is proportional to the cube of wind speed, meaning even small direction errors or delays can cause significant energy losses. My next slide is system architecture. Our system includes three primary hardware components: the RS485 wind vane sensor outputs analog signals corresponding to wind direction. The cup type ammeter measures wind speed via pulse output, and Arduino Uno reads both sensor, compare the yaw error, and triggers a stepper motor if the misalignment exceeds plus or minus 50 degree and wind speed is above 3 millisecond meter per second. Here, here is how the logic flows. We first read the wind direction and speed. If the wind is below the curtain speed, the system holds the current position. If wind speed is acceptable, it calculates the yaw error. If the error is above plus minus 15 degree, the motor rotates the knuckle to realign with the wind. The system then updates its position and reevaluate after a short delay, maintaining continuous tracking. My next slide is hardware integration. The complete hardware system includes an Arduino Uno R4 Minima, offers advanced processing power, the RS485 WinVan with Modbus protocol, a, a DevMo 5-volt stepper motor, and ULN 2003 driver for precise yaw actuation, a DC-DC converter to stabilize power supply from 12 to 24 volt battery sources. All components are mounted on a mechanically stable yaw platform that can rotate 360 degree, ensuring flexibility and real-world usability. Next one is the performance results. Our testing demonstrate promising results. The system achieved via accuracy within plus minus 10 degree. The motor operates less than 10% of the time, which prolongs its life. We observed improved energy output under variable wind condition compared to static wind orientation. This indicates that our system not only works but also offers tangible performance benefit. Future work. Uh, in terms of future work, we plan to move forward with the hardware implementation of the system. After building it, we will first test its performance in a controlled environment to check its accuracy and response to changing wind direction. Once the system performs well under those conditions, we will conduct real world field testing. This will help us validate the system's reliability, responsiveness, and effectiveness in nature wind condition, preparing it for practical renewable energy applications. Next slide is conclusion. To summarize our work so far, we have completed the design and component selection for a real-time wind tracking system. This system is intended to improve the efficiency of a horizontal axis wind turbine by ensuring it stays aligned with the wind direction. We used a combination of wind direction sensor, aminometer, microcontroller, stepper motor, and motor driver. This setup helps reduce mechanical stress and power loss, especially when wind speed are above the cut-in threshold. Overall, the design ensure more consistent energy capture and better turbine performance. Thank you so much.